So let's, where we ended off last week, we were looking at electric circuits and seeing how resistors can be analyzed in a circuit, whether they're in series, one after another, or parallel, where the current can go to either or. And the goal with doing these, we looked at the two most basic examples you could have with only two resistors. But no matter how complex a circuit gets, the goal is to first reduce it into a single resistor. So we just want to reduce it to one battery, one resistor, with the equivalent resistance of the circuit. And there's a lot of ways to think about it or phrase it. Like one very imprecise way might be to say like the resistance that the battery feels is what we want to put in there. But really what we're talking about is the total current. We want to replace all the resistors in the circuit with a single resistor that will produce the same total current, right? Because the battery doesn't know what's happening in the rest of the circuit. It just feels this resistance, and as a result, with that voltage of the battery and that equivalent resistance, whether it's made up of the more complex arrangement of circuits or a single equivalent resistor, those two things produce whatever the total current is. And then once we get that total current, that's the key piece of information we need to then build back out and find the behavior at each individual part of the circuit. What's the voltage drop at each one of the resistors in series? What's the current through each of the resistors in parallel? So that's what we're going to work on today and do a couple examples. So just to review what we found about these things, resistors in series, so one after another, share a current. And we can see that just from conservation of current. If the current goes through R1, there's nowhere else for it to go but also R2. We can't avoid either of them. All of the current goes through both. And so I total, I1, I2 all mean the same thing. There's only one current occurring in this circuit. And as a result, we found that the equivalent resistance of resistors in series is just the sum of whatever the resistances are. And this generalizes to as many resistors as you have in series, you just add them up. The key things to remember again are the current is shared, the same current for resistors in series, but the voltage drops do not have to be equal. They certainly could be if the resistances are equal, but let's say I have a 10-volt battery and the voltage drop across R1 is 6 volts. That just tells me that the voltage drop across R2 has to be 4. No matter what, when we go through a whole loop, we have to lose all the voltage we gained from the battery, satisfy the loop rule, get back to 0. So there's nothing that says they have to be equal, but we do have that relationship that their voltage drops have to add to get the voltage drop of the battery. Moving over to parallel resistors, we have kind of the opposite, where they do not necessarily share a current. In fact, they might have the same current if they're, again, equal resistors, but they're different from I total. And same thing, this comes from the continuity equation, just conservation of current. We have I total coming into the junction, and then some of it goes to one branch, some of it goes to the other. And so that means that the total current has to just be the sum of whatever current splits up into each one. And then when they come back together at the final junction, then those two will add back up into whatever total current. So it's still, the argument is made by conservation of current, but because of the arrangement, we get a different result. And we kind of rushed through last time, but the equation was there that the relationship between the R equivalent and the resistances themselves is this, which looks kind of similar to the one for a series, except now everything is its inverse. So there's an extra step or two in solving it. But a key takeaway of that equation is that also I just think I realized I forgot to record the audio. Oh no, I did. Never mind. That'll be a fun Easter egg for the video. So the resistances add this like inverse manner, and what we find is that the equivalent resistance is actually lower than any of the individual resistors that are added in parallel. So clearly for series, the equivalent resistance is higher. We're just adding one after another. But in parallel, we're giving more options for the current to take, and so the equivalent resistance goes down. And that's just a product of this equation, but we'll also talk about it in a little more detail soon to maybe illuminate why that intuitively makes sense as well. So the keys for resistors in parallel are that they do not share current. The current is split between them. And they do share voltage.
So that's the other key piece, or very important, yeah.
Since you're saying that for the parallel resistors, like R is, or like REQ is less than, does that mean that like the voltage drop is like less than usually in like a series then?
We'll take a look at that. The voltage drop has to be the same. So actually, I was just about to, we'll talk about that. So the voltage drop across parallel resistors still has to satisfy the loop rule. So if I have a 10-volt battery here, and I go through a loop just through R1 and back to the beginning, that means I have to have a 10-volt voltage drop across R1, right? It doesn't matter about R2 being there. That's a valid loop just through the battery in R1, and that has to satisfy the loop rule. Same thing separately for R2, that if I have 10 volts from the battery and take R2, then I also have to have a voltage drop of 10 volts. So these voltage drops have to be equal, and that's also equal to if I replace them with an equivalent resistor in their place that has the whatever equivalent resistance from this equation. I'm still, after replacing that, need a voltage drop across that equivalent resistor that's equal to the voltage drop across the battery in this case, because I have to satisfy my loop rule no matter it's one of these two paths or the equivalent resistor.
Like what I was asking was like if you were to have a choice between constructing a parallel circuit and a resistance, you don't want to like lose as much voltage. Is a parallel like?
Well, the next slide maybe we'll talk about a little, but no matter no matter what, you're going to lose the same amount of voltage. So I could, if I have a battery that's connected to a circuit, no matter what, we're going to lose all that voltage just because of loop rule. But current, yes. If I wanted to maximize my current, then I'd want to minimize my equivalent resistance, and yeah, maybe I'd want to choose parallel. Okay, so let's put this into practice a little bit. So a quick clicker question. So assume all of these resistors have the same value of resistance. They're all identical, and we're just combining them in different ways. Which one of these setups has the lowest equivalent resistance? I guess this is understandable, but there's a lot more discussion that occurs in this class than in the A section at like 7:45. And as soon as I recognize the discussion, it like builds up, which is great. But I'm going to stop us there. I know we're still working on it. So let's walk through it. The answer is D. So we did really well on this. Let's talk about why. Well, if we let's just evaluate the equivalent resistance for that one. We have our equation. We don't know what the resistance is. We just know they're all equal. So we'll just call them R. And then on the right side, 1 over R plus 1 over R plus 1 over R. We get 3 over R. And then that crucial step that we will all forget at some point in our time here, we have to flip it. So our equivalent resistance is R over 3, which is kind of counterintuitive to me at first, right? We have one resistor with a value R. And then regardless of how I set them up, I would think that if I just add more resistors, the resistance is going to increase somehow. But clearly that's not the case. It went down to 1/3 of its original value. So the way I like to think about it is that we just open up more pathways for the current to travel down. And I think I talked about this last time, but if you think about it, the current trying to get through the circuit as people trying to travel through a hallway, if you have a single hallway that's 10 feet wide, that's its resistance. So you try to send a huge mass of people through there, they're going to struggle and face that limitation of space. But if I add another 10-foot hallway in parallel to it or right next to it, then some people are going to go that way as well. And so even though I introduced another pathway with its own resistance, I gave more channels, and so it's less crowded, and so it's easier for people to get through. Or in the circuit case, there's less equivalent resistance. That this makes it easier for the current to pass through this section of circuit because they can each charge can go a different way. So then if we just expand this reasoning to the other pieces of the circuit, A, we have 2 in series. We know those just add, so 2R is certainly greater than R over 3. For B, we have 1 in series with 2 in parallel. So for that one, we need to start with the 2 in parallel. I'll talk a little bit more about why, like how we decide where to start on the next slide. But if we combine those 2 in parallel, we get R over 2. Same math over here, except just missing one of these pieces. So that's one little insight too, that combining 2 in parallel lowers the resistance sum, and putting 3 in parallel lowers it even more. So if I added another R over 4, if I added another R over 5, that easy little R over the number relationship only holds if they're all equivalent, if they're all the resistors are equal, but in this case that's true. So anyway, back to B. We have 1 plus a half, so that's 3 halves R, still a lot bigger than R over 3. C, we have a half R plus half R, R, which is clearly bigger than R over 3, and then E is just R as well. So all of these are bigger than D. D is just 3 pathways that reduce the equivalent resistance to R over 3. So this problem was meant to help you kind of bridge the gap between doing the math, which you certainly will have to use this equation a lot and see the results, but then also it's good to have some intuitive sense while you're working through these circuits. If I have resistors in parallel, then my output, my equivalent resistance for that section, for those branches, should be lower than the resistance of any one of them. And we'll see that in a sec. So again, it's good to be able to kind of flip-flop between this quick reasoning and being able to prove it, and vice versa. When you do the math on something that you don't have a good intuition about, trying to piece back together why that equation makes physical sense. So let's do a more complex example together. So now we have a circuit with a combination of series and parallel, and we're going to have to, as we said at the beginning of the lecture, simplify this down into a single equivalent resistance, find our I total, and then work backwards to find behavior like the current in this branch, voltage drop across individual resistors. We're just going to basically solve everything you can about this circuit. So this kind of addresses that question that I mentioned on the last slide, which is where do I start? Right? A lot of times we just get a circuit with a lot of different combinations of resistors, and it's not really clear how to attack it. And I guess the answer is if you don't break any rules, then however you choose to do it is correct. And in this case, there's only one way to combine these, one order to combine these in a way that doesn't break any rules. So those rules we kind of talked about, but we didn't maybe explicitly state them. So if I'm combining resistors in series, I can't cross a junction. Another way to say that is if I'm combining resistors in series, they have to have the same current. We know that's true of resistors in series. So 2 and 3, I could certainly combine these in series right off the bat, right? Just all the current that goes through R2 also goes through R3. Great, these are in series, I can just add them. But what if I didn't see that? What if I wanted to first combine R4 with R5 in series? Well, I can't do that because R4, well, first of all, we have to cross a junction. So there's a nice visual rule that we cannot do when combining things in series. But also, R4 has a different current than R5. Some current goes through R4, but then it's joined by whatever current went through that top branch, and so a different current passes through R5. So we cannot combine these two resistors in series. And the same is true about R1 and R2, or R1 and R4, anything like that. The only ones right off the bat that we can combine without crossing a junction in series are R2 and R3. We can also ask ourselves, why can't I start by combining the bottom branch with the top branch in parallel? Well, R4 is not in parallel with just R2, or R4 is not in parallel with just R3. It's in parallel with this whole branch, right? So the voltage, I guess, same thing. We know about resistors that resistors in parallel, that they share a voltage drop, or branches in parallel that share a voltage drop. And R4 does not share a voltage drop with just R2. It does not share a voltage drop with just R3,
it shares a voltage drop with this whole branch. In other words, these voltage drops are going to add to equal this voltage drop because we need the same answer for the voltage here and the same answer for the voltage here, no matter which path I take. So, long story short, we cannot start by combining R4 in parallel with anything. And the only thing that leaves us with is combining these two in series. So maybe that looked like an obvious choice from the start, maybe it didn't. But either way, even if you wanted to just exhaust all of their options and you just started picking pairs at random or picking like sets of them, if you don't break any rules, there's only one option here. Sometimes there will be multiple options, like if there were also two resistors in series in the bottom branch, then it doesn't matter whether I combine these in series first or these in series first. Neither of those breaks a rule, and so it's fine. So let's do that. We combine those two resistors in series. We know their resistances just add. So 5 ohms plus 2.5 ohms, we get 7.5 ohms, and we'll call that R23, which is the equivalent resistance for just that branch. Now, our next step, we can try a bunch of different things, but there's nothing we can combine in series just yet, right? Because I can't go R1 to R23, I can't go R1 to R4, I can't go 2, 3 to 5, so on. The only thing that I can do without breaking a rule here is combining R23 and R4. Now we just have these two parallel branches, one resistor in each. Yeah.
We have connected R1 to R5.
Yes, so there's nothing wrong with that. At this point, if we wanted to, we could see that R1 and R5 both have the same current, and we could just add those two up to get 35 ohms. I would avoid that. Well, not necessarily avoid it. I didn't go that way because if you have a more complex circuit where maybe there's like one junction and then within one junction another, it just gets, I can see a situation where you find yourself thinking two things are in series but they're not. So I like to go sequentially, but yeah, technically there's nothing wrong with that. Thanks. Okay, so let's combine those two in parallel. I'm not going to work through the math, but we can check it. Right? I'm saying that if we use that 1 over REQ equals 1 over R1 plus 1 over R2, we can solve that our REQ, which I'm calling R234 EQ, is 3 ohms. And is that less than either of these resistors? Yeah. We have a 5 ohm resistor, and then let's say we add a 7.5 ohm resistor in parallel. Even though the 7.5 ohm resistor has a higher resistance than that 5 ohm resistor, we still opened up some other pathway for the current to take. And so it's still easier for the current to get by, or the equivalent resistance lowers. To move that into the hallway example, it's like we have a 10-foot wide hallway that we're sending people through, and then right next to it, I put a 4-foot wide hallway. Even though the 4-foot wide hallway is more difficult to get through than the 10-foot hallway, some people are still going to take the 4-foot hallway. And so it still makes it easier for the people to get through. It still makes it easier for the current to get through anytime I introduce another resistor. And what that reasoning leads us to is that not only does our R equivalent lower the resistance, the R equivalent should be lower than any of the resistances that are in parallel. So I can have, 3 resistors in parallel, 1 ohm, 10 ohms, and 100, and the equivalent resistance would be less than 1 ohm. Yeah? 3 from like 1 over 5 plus 1 over 7.5, like this equation. I just plugged those in. I just didn't show it here. Okay, whoops. Yeah, okay, that's where we were. And now we're left with 3 resistors in series, right? That's just one after another. They all have the same current, and so we can just add their resistances together to get a final REQ of 38 ohms. So now we've succeeded in the first step, which is simplifying. Yeah?
At what point can we combine R23 and R4?
At one point, why can we?
Like, when can we not? Like, what's a rule that we know
Oh.
it can?
Gotcha. If they don't share a voltage drop. So that's how we know that resistors, I don't know if this works both ways, but we know that when resistors are in parallel, they share a voltage drop. And so, for instance, here, R4 does not share a voltage drop with either one of these individually. It has the same voltage drop as the sum of those two. So we have to combine them. But now, the voltage drop across R23 is equal to the voltage drop across R4. Okay, so now we have our fully simplified circuit, and now we can find our total current, right? We just have a battery and a resistor, easy. So here's our circuit, and we can write down our loop rule. We go through the battery, and we pick up epsilon, the voltage of the battery, and then whatever voltage we picked up there is going to be lost across this one resistor, minus I total times R. And so I can solve for I total, 19 volts over 38 ohms, and we get half an amp. So now we know that not only in this circuit, it is true in this circuit, that this, if I set up a 19 volt battery with 38 ohm resistor, I'll get half an amp current, but that's also true for all four of these equivalent circuits. Even though they all look different, the whole point was that each one of these is equal, or gives the same I total, feels the same to the battery as the last. So here we'll have half an amp, here we'll have half an amp, here we'll have half an amp, here we have half an amp total that's coming out of the battery. But as we work backwards, we'll find that that half an amp can split when we get to the parallel section. And now we're going to have different voltage drops across each one of these resistors. So we can find that like intricate behavior instead of just saying throughout all the resistors we'll lose the 19 volts. We can see what's really happening. So let's take a step backward. Take a step back to then when we just had 3 resistors in series. So now we know, we figured out that there's half an amp going through this, and there's nothing special going on here. We just have resistors, and we know that the voltage drop across resistors is just minus IR. So for delta V1 across R1, it's just minus I total times R1. That comes out to 10 volt, minus 10 volts. For delta 234, same thing, but subbing in 3 ohms, we get minus 1.5 volts. For delta V5, very similar. And so we get 3 voltage drops. Again, we're plugging in I total for all of them because in this version of the circuit, the current is the same everywhere. There's nowhere for it to branch off. So I total applies to every resistor. And just as a check, we can add together these delta V's and see that they come out to negative 19 volts, satisfying the loop rule. So if we go through the battery, pick up positive 19 volts, and then as we pass through all of these now three resistors, we will lose the 19 and get back to 0 to satisfy the loop rule. All right. Yeah.
So for our battery, is like in the other case, that is like just one small line and one plus one.
Yeah. So batteries will often be drawn either like this or half of this with just one large and one small one. That's the same thing. You could see 2 batteries in a circuit, but it'll be clearly labeled. What did you say? Yes, and we'll see examples, and when one's backwards, and yeah, we'll work through that. Okay, so let's take one more step back. Now let's expand this R234 equivalent into R23 and R4, the parallel branches. Now here, we know that the current is not going to be the same in the 2 branches. Instead, it's going to split, and the sum of the currents in the 2 branches will equal I total. The other thing we know is that the voltage drops are the same. Right? Not only is the voltage drop across the top the same as the voltage drop across the bottom to preserve just the fact that there's one voltage here and one voltage here, but that's also the same as the voltage drop we already found for the equivalent resistor. So if I just took this circuit and drew a black box around this parallel segment, by finding the equivalent resistance, we're saying that you can't tell whether or not I put these 2 resistors here in parallel or their equivalent resistor there. They're both going to produce the same behavior, or the same voltage drop. So if my voltage drop across the equivalent resistor is minus 1.5 volts, then the voltage drop across this setup has to be 1.5 volts. And we know that in parallel, all of the branches have to satisfy that, because the current only takes one branch. Right? It's okay that both of these have that voltage drop, because the current doesn't go through both. It just picks either one. And either way, if we go through the loop rule, that section is responsible for that minus 1.5 volts. So now, knowing what the voltage drop has to be in each branch, we can figure out what the current is. How does the current split up between these two branches? Because now I know the voltage drop, and I know the resistance, so I can solve for the current. So before our unknown was voltage drop, now our unknown is current. And if I plug in for R23, divide the 1.5 volts by the 7.5 ohms, I get 0.2 amps. So that's how much of the current goes to the top branch. I could do the same math and just swap out 5 ohms for R4, and I'll get 0.3 amps. So what we found, and that does satisfy our continuity equation, 0.2 plus 0.3 is indeed 0.5 amps. So we come in with 0.5 amps, some of it goes to the top, some of it goes to the bottom, and then we come back together, they add back up to 5 amps. So continuity, conservation of current is all satisfied. And then the other interesting thing that I guess we would expect is that R4 gets more current than R23, right? I4 is 0.3 amps, I23 is 0.2 amps. The reason being, this branch is easier to go through for the current. It has a lower resistance. So we often hear probably the phrase like the path of least resistance, and this is physically where it comes from. And it's literally true here, that more of the current will take the path of less resistance. Right? Some is still going to the top, but more will choose the bottom because it's easier. Just like more people will choose the 10-foot wide hallway than the 4-foot wide hallway, but some people will still go to both. Okay, I'm not going to take the extra step of just splitting up R23, but we know how to do that. We know this branch is responsible for 1.5 volts of voltage drop. We know the current here. The current here is now 0.2 amps. So if I know these resistances, I could just do minus IR to get the delta V, but we know whatever those two voltage drops are separately, the R2 and the R3, will add together to get minus 1.5 volts that we have to have. So this example hopefully showed just a relatively complex or kind of medium complex circuit, us boiling it down to REQ, finding I total, and then working backwards to find how the current breaks up for parallel resistors and how the voltage drops distribute for series. The one thing this doesn't really show is an example where the circuit is drawn in a confusing way. Which that's something you might have experienced already a little bit, but you certainly will. There's ways to draw circuits that just kind of make your mind think that it's going to behave differently. The example that I always point to is like, if you have, I don't know if you've seen it yet, but it kind of looks like a butterfly. You have a battery in the middle, and then it branches off in two separate directions with like one resistor over here, one resistor over here, and then they come back together and meet the battery on the other side. That behaves the same way as just two resistors in parallel. I could go this way and get to back, or I could go this way and get back. They have the same voltage drop. They have a starting junction, an ending junction. It's all the same. But the way it's drawn, it just, I don't know, it messes with my brain. So we just need to practice those and make sure that we can develop our intuition to kind of make these problems easier and maybe a little quicker. But when that fails or isn't quite enough, we have these tools to work with, like, okay, I know that if they're in parallel, they have to share a voltage drop. Is that true? Am I crossing a junction here to combine these in series? Can I redraw the circuit and make it have the same behavior? All these things we'll practice with. But so it does get more complex than this, but not technically, just kind of visually. Okay, so actually this next example kind of showcases that a little bit. We're going to look at the phenomenon of shorting a resistor. So here we have a circuit that should look pretty simple to us. We have current flowing through one resistor, and then there's a parallel section where R1 and R2 are in parallel. They come back together. We've seen something like this before, but what if I put in another wire here? So I put this red wire that looks like it's going around R2, and now I've added another path, so I could go R2 or this other path, but this path has no resistor. So that's what it's called when we short it. So naively, before maybe we could guess what happens, but let's try to just use the equations we have available to us for branches in parallel and see what we can figure out. So is this wire in parallel with R2. Yeah, right? Because here's the starting junction. I could either take this wire or I could take R2. So those two look like they're in parallel. But the trick here is that it's actually also in parallel with R1. Why? Well, here's a junction. I mean, I guess there's two junctions, but coming out of R3, I could go down all the way through this red wire and back up and never go through R1, or I could go through R1 and never go through this red wire. So this wire, the way I've drawn it, looks like it's shorting out or in parallel with R2. But in reality, it's in parallel with R2 and R1. So we would consider these three branches all in parallel with each other. So this is maybe the most basic case of it, but it's just somewhere where I can just change a drawing a little bit and make it that much more difficult to understand. But anyway, let's try to analyze this. So we know our equation for combining branches in parallel. Right? We have 1 over R1 plus 1 over R2, but then 1 over 0. There is no resistance in this branch that we added. And so I wouldn't recommend writing this equation. Like, we'll never have to actually write this out again. But if we try to push this a little further, I know our calculators and math teachers don't like it when we write 1 over 0. But really what it means is like infinity. 1 divided by 0 is infinitely huge. And as a result, we get that to satisfy this equation, R12 also has to be equal to 0. So the equivalent resistance of these three branches in parallel, one of them without a resistor, is 0. So that basically what happens is we introduced an infinitely easy path, a path of infinitely small resistance, and as a result, all of the current goes that way. Usually we just have larger and smaller resistors, and so some goes one, some goes the other, more the easier path, less on the difficult path. But in this case, we have an infinitely easy path. And so in that case, all of the current goes that way. None of it chooses to struggle when it doesn't have to at all. And so the R equivalent for the whole circuit is just going to be R3, because this does not short R3. No matter what, when I draw a loop rule, I have to go through that. So that's the equivalent resistance for this whole circuit now is just R3. So shorting a resistor in the end makes it look like it's not there. So this circuit will behave exactly like R1 and R2 are not there. And so if a blank wire, a resistorless wire is in parallel with any amount of resistors, they are shorted or kind of removed from the circuit. So let's do a clicker question on this. This one's kind of tough. Well, maybe not. I don't know. 3 identical light bulbs are wired to a battery. What happens when a wire is added, as shown? And just to remind you, the brightness of a light bulb is determined by the power dissipated by it. And I put the expressions up at the top if you'd like those. So what happens to the bulbs if I add this wire here? All right, maybe this one wasn't so hard. I'm going to stop us there. The next one is the harder one. That I remember. So let's go over this real quick. We add this wire here, which, like we discovered on the last slide, is going to short out light bulb 3, but also short out light bulb 2. Because if I go through the circuit, I can pick a loop that avoids both light bulbs by going through this resistorless wire. And so this circuit will behave just like it was the battery and light bulb 1. So 2 and 3 are definitely going to they're going to go out, right? Because now there's no current going through them. So our I is 0. And also if our current going through them is 0, that means delta V, which is just IR, is also 0. So 2 and 3, those go out. Then what's going to happen to 1? Well, if we think about it from a voltage drop perspective, we have the voltage of the battery, and before we had to lose some voltage across the branches that had 2 and 3, and then lose the rest across 1. But now I lose all my voltage across the light bulb 1. And so if we look at maybe the furthest on the right expression for power, that's just delta V squared over R, we just argue delta V is going up, and R isn't changing, the resistance of light bulb 1. So the power dissipated increases, and the bulb in light bulb 1 gets brighter. You could also argue that a different way. We could say, like from a current perspective, if we look at the equivalent resistance for the whole circuit after I add the wire, it goes down, right? Because before, even though 2 light bulbs in parallel have some lower resistance than just 1, they still add something. Having those light bulbs there adds some amount of resistance. I guess it would be R over 2. But now that I took that away, the equivalent resistance for the whole circuit goes down because we removed that obstacle for the current. And so if the overall resistance goes down, the total current in the circuit is going to go up. And for that, we can look at maybe the I squared R version of the power equation. Now I is increasing, R is staying the same, and so our power dissipation goes up. Those 2 lines of reasoning were different, like we focused on different values, but it's just to emphasize that all of these things can be figured out from one another. Like these 3 equations mean the same thing, they're just subbing out, because we know the relationship between delta V, I, and R, and so we can get back and forth between either one of these. It just boils down to either whatever's more intuitive for you or whatever's more convenient based on the numbers you have. But we could choose to do it any way we'd like. Like I guess we just argued that I and delta V go up, so we could do all of that reasoning together and then use that first equation.
So if we did have the bottom wire there with the voltage that's going up, or the current, whichever one, that goes to 2 and 3 would be equal, and therefore that goes to the regardless, if we didn't have that wire on the bottom.
If we did not have this wire on the bottom, then you're right that the current going through 2 and 3 would be equal. But in that case, the voltage drop across 2 and 3 would be lower than the voltage drop across 1.
So they would all be lighted, but one would be the brightest.
Exactly.
Oh, sorry.
Okay, now the next one is more difficult, I promise. So I'll give you maybe 2 or 3 full minutes with this one. And I would definitely recommend using equations. But now, light bulb 3 burns out. So the short's gone, but light bulb 3 burns out. In other words, we just cut the wire. No current can flow through this branch. What is going to happen to the other 2 bulbs? All right, I'll give you 30 more seconds. All right, I'll stop us there. So the answer is D, that 2 gets brighter and 1 gets dimmer. So let's walk through why that is. Okay, so first, what happens when light bulb 3 burns out to the equivalent resistance? Well, before, assuming they're all the same light bulb, before it burned out, we have 2 and 3 in parallel, which we saw earlier that just 2 equivalent resistors in parallel turn into whatever that R was over 2. We double the amount of pathways that it has. So now this is R over 2 plus just a single R for 1. Our equivalent resistance is 3/2 R. But then light bulb 3 burns out, and now we actually have a much simpler circuit that's just current going through 2 and then current going through 1. So they're in series, and we just get R plus R, or 2R. 2R is greater than 3/2 R, right? So when the light bulb burns out, the equivalent resistance of the circuit actually goes up because we reduce the amount of pathways that the current has. And so if the equivalent resistance goes up, the total current in the circuit is going to decrease, right? Because we have to still have the same voltage drop going through the circuit, and so the total current is going to decrease with this increased resistance. So if we just look at light bulb 1 first, all of the current goes through light bulb 1, right? Has nothing to do with the 2 resistors in parallel, or maybe something to do with them, but it's not in parallel with them. So all of the current every time has to go through light bulb 1, and so if I total goes down, then the voltage drop across 1 also has to go down, right? If we look at the power dissipation one, we could also look at just I squared R as the power dissipation or the brightness of light bulb 1, and if I goes down, then 1 has to get dimmer. So 1 indeed does get dimmer, and as a result, like the voltage drop also goes down. But all this just comes from the fact that now that the equivalent resistance of the whole circuit, since that went up, the total amount of current flowing through went down. Light bulb 2 is a little bit more tricky. One way to think about it, this doesn't really answer the whole story, but if we just look at the current splitting up between here, before, when light bulb 3 was operating, light bulb 2 only got half of the current, right? Assuming they're equal, light bulb 2 gets half, light bulb 3 gets half. And so that's some current and some power dissipation for light bulb 2. But when light bulb 3 burns out, light bulb 2 gets all of the current. So we just went from getting half of the current to getting the entire current. So that would make us think that light bulb 2 is going to get brighter, but we still don't technically know that because the current itself is changing. We're getting all of it instead of half of it, but we know the current did decrease itself, so we have to compare those two. One way to think about it, we just proved that it's going to get twice the amount, twice the proportion of the total current that it was before, but the current only decreased from 2 to 3/2. So the current decreased 25%, but light bulb 2 is still getting twice the amount of that it would have. So, I mean, that's one form of reasoning that we can use to argue that light bulb 2 will indeed still get brighter because it's getting more current. Another way we can do is look at the loop rule here, where no matter what, I have epsilon, and then I have a delta V2, so this is one valid loop, whether or not light bulb 3 is illuminated. Going through epsilon, then through delta V2, and then through delta V1 has to be a valid loop rule, right? So if V1 goes down, we argued that first, that since the total current decreases, the voltage drop across 1 goes down. In order for this loop rule to still make sense, to still add up to 0, epsilon's not changing, so delta V2 also has to go up, or not also, but delta V2 has to go up to make up for the drop in delta V1. So I think that's maybe less direct but easier way to see how we know for a fact that light bulb 2 is going to get brighter. And again, from the voltage, we could just use this third equation here that doesn't depend on current. Delta V squared goes up, R is not changing, it gets brighter. Okay, questions on these? I like these problems because they're just very simple little changes, but they really force us to think about what's happening. I really recommend that for these two especially, and maybe the big circuit simplification and simplification that we did before, you use that circuit simulator. I think there's a link to it in the DL and on my last lecture and on Piazza. And if you can't find it, just ask us. But it's really helpful to visualize the current flowing through a circuit, and where you see like more current flowing through, or it slows down or bunches up, it does a bunch of stuff that makes it easy to see what's happening. And you can experiment by taking a light bulb out, adding one in series, looking at all the values as well. It will like give you an ammeter and a voltmeter. You'll do this in DL, but yeah, practice really helps. Okay, questions on any of the circuit stuff, because we're about to zoom out a little bit and talk about something else.
So you said, can you repeat which one gets brighter and which one gets dimmer?
Yeah, so 1 gets dimmer, 2 gets brighter. Okay, so now we're going to zoom out a little bit. We talked about fluid flow, we talked about electrical circuits, and now we talked in between those about the similarities, right? We used fluid circuits as a way to transition into electrical circuits, and the commonality between them came from the fact that in both cases we have this difference in energy density, whether it's density talking about energy per unit volume, or density for electrical circuits talking about energy per unit charge. But whether we're talking pressure or voltage, it's still some energy density, and we have some gradient, which is just some difference, really, high and low. And that difference between energy densities in two spatial locations causes a flow from high to low. They want to balance out, come to equilibrium. And the flow rate is determined not just by the degree of that difference, so like the differential of high pressure to low pressure, high voltage to low, but also the resistance in between. In both cases, there is some resistance, and the balance between whatever that difference is and the resistance, maybe a pump if you include that in here, determines whatever our flow rate is going to be. Higher resistance, lower flow rate. Higher differential between the energy densities, higher flow rate. So this chart here shows the first row is this. So this equation at the top is one we've seen before, except phi now is just like this general variable. We could plug in there pressure, or really, if we want to be more precise, delta, like head, right? Because we have pressure, potential energy density, and kinetic energy density. But for simplicity, you can just think about that as pressure. Or we could substitute in V. We have delta V equals minus IR. That's an equation we saw. We know how it works. But now we could also apply that to other systems where we have differential energy density, and then that causes a flow, like heat. If we have a difference in temperature, high temperature in one place, low temperature in another, and put them in contact, we're going to get heat flow between them that tries to balance out that temperature difference and take heat from the high temperature area to the low temperature area. And the resistance is that in that case is like your coat or a cooler or something like that, any insulator. And then we could also apply it to something like diffusion. If you have a high concentration of ions and a low concentration of ions and a membrane in the middle, there you still have that differential. In that case, I guess it wouldn't be energy density, just density, and they're going to even out. We're not really going to talk about the diffusion. There's a couple slides on the diffusion stuff if you want to take a look, but we're not going to cover that a lot in this class. I know something you probably see a lot in bio courses. But we're going to talk a little bit more about this linear transport model in terms of heat. So another thing to keep in mind is that so far we've only been talking about steady state. That's a term we haven't used with electricity that much, but all of these systems have still been steady state. The current, the voltage drops, everything stays the same at every point in the circuit in time. We're just talking about spatial changes. And so steady state in this general context just means that delta phi stays the same. In other words, I have a high energy density and a low energy density. That causes some flow, but we're assuming that those two don't change. We know that's not really realistic, right? If we have a high temperature and a low temperature and heat flows in between them, The high temperature is going to come down, and the low is going to come up. They reach equilibrium. But so far, we've been ignoring that. Assume that they're like thermal reservoirs or whatever. There's plenty of water to run for ages. It doesn't matter, but we've been ignoring that change. We'll go there next week and see what happens when delta phi is not constant, not steady state. But for now, we will. So skip through this. All right, so let's just do one example with heat transfer real quick. So heat transfer works, like I said, the exact same way as before, except now. So this equation that I'm showing right here is really the same as I equals delta V over R, except P here, sorry, I know we use P for other stuff, but here, P here is just power. It's just energy density per unit time, energy per unit time that's being transferred. And so what we're saying, so that's our flow rate. Power is the flow of energy. Delta T is just the temperature difference, and R is our resistance. So the greater the temperature difference, the higher flow rate of heat. The greater the resistance, the lower flow rate of heat. So this is a model that, even though we just started talking about it, we already pretty much know everything about it. And the value of R just depends on whatever the material and the configuration, right? If you're talking about the flow rate of heat between your body and the air around you, one resistor could be a shirt, one could be a puffy coat. They're both going to have different values of R. Yeah?
So when you were saying that it's like a steady state, like the temperature, we're ignoring it?
We're not ignoring that. We're just saying that the temperature difference doesn't change. So like if I have, well, this next example shows where it's not happening. So yeah, I'll ask your question again at the end if this doesn't help. But so there's a long example. I'm not going to actually pose this question to you. Maybe you don't even need to read it. But basically what I want to show you is using this energy density model, or linear transport model with heat flow to apply to a real life scenario. And the scenario really quickly is you have a hot cup of coffee and a cold splash of cream. And you're at your house. And you're going to go to class and drink it. And you want the coffee to be as hot as possible. Should you combine the coffee and the cream first, like cool it down a bit at your house, and then bring it to class and then drink it? Or should you keep them separate and then go to class while they cool off separately and then pour it in at the end once you get to class, right before you drink it? Which one of those will result in a hotter cup of coffee? So this example is not steady state because the temperature difference is changing. As the coffee sits or travels with you, it gets cooler. And we're running out of time, but the answer is that you should add the cream first. This graph you can try to disentangle for yourself later, but just intuitively the answer is you want to cool the coffee down first because then the temperature differential is smaller. So that the whole time you're going to class, the delta T is smaller, and so the heat flow is less. Whereas if you wait till you get to class, the whole time the coffee is hotter, and so it loses more and more heat at a higher rate. And then when you get to class, you pour the cream in, and it shocks it down to below what it would have been if you just poured the cream in first. So there's lots to unpack there, but you're not going to be tested on this. We're still going to just stick to electrical circuits. This was just a bonus.